Hello, thank you very much for attending our second workshop. Let me share my screen. Compartir. Compartir. ¿Qué pasa? Porque no me deja compartir. I cannot share. This is our workshop, second workshop on DOiT 3D micro. This is a plenoptic eyepiece for transform any optical microscope into a 3D lightfield microscope. I am Ángel Tolosa. I am the CTO of and co-founder of DOiT Plenoptic. And DOiT Plenoptic is a spin-off from the University of Valencia, founded in 2018, with the aim of bringing 3D imaging technologies to everyone and for every instrument for a subjective observation. Our first product is this, the plenoptic eyepiece. This is a device that can be attached to in the eyepiece port of a conventional microscope to transform it into a 3D digital microscope. We are a young company, but with a strong knowledge in. We are physicists, we are engineering, and this is our first product, the plenoptic eyepiece. A key advantage of our technology is that we can take 3D images in a single shot. So we can take the 3D information of the samples in real time. The core of our technology is that called lightfield imaging. Lightfield imaging is based on take a lot of perspectives in the sample using a microlens array in front of a conventional sensor. Typically, this has been done in two ways. One is the focusing mode, and the other is the unfocusing mode. Focusing modes are based on projecting the object plane in front or behind the microlens array, and then the microlens array focuses the microlens in the microlens array focus the image on the sensor. Unfocusing mode is based on projecting the object plane just on the microlens array plane. This way, the images are unfocused on the sensor. A key aspect to take account when we take lightfield images is that we need to limit the field of view of the images by using the main lens. This is represented here with the blue line. This means that the numerical aperture of the main lens and the numerical aperture of the microlens array needs to match. This is a constraint when we use conventional lightfield imaging in microscopy, because the aperture of the objective changes with the objective. The need of matching the numerical apertures can be seen here. This is the correct matching. This is an over matching. Then the elemental images overlaps, and we lose information around the images. And in this case, in the field of view is smaller, and then we lost information of the sample and effective pixels. To avoid this, we use a new paradigm of light field capture, in which we take directly orthographic views. In this case, the object is at the focal plane of the main lens, and the field of view is limited by an independent field stop. Here we have the advantage that we can place the microlens array at any plane along the optical axis behind the main lens, keeping always the image focused and the image of the field stop at the same size. This concept was used by Gabriele Scrofani to develop the Fourier integral microscope. This is the scheme he used. We have the objective of a microscope. We have a relay lens, the field stop I said before, the lens I said before, and the microlens array. As we can see, and if we saw in the scheme of a microscope towards the eye, we can see that we have the objective, we have the tube lens. The focal length of the tube lens depends on the mark of the microscope. The tube lens forms an image in front of an eyepiece, and the eyepiece projects parallel beams, parallel rays towards the eye of the observer. A key thing to keep in mind when we design an eyepiece is to keep this distance in a proper the eye relief, the distance in which the aperture stop of the objective is projected behind the eyepiece, to a certain distance in which the observer can see without artifacts. This will be not close to the eyepiece, but not far away from the eyepiece. Exploiting this concept, we think, and the scheme proposed by Scrofani, we thought, okay, we can replace the eye by a microlens array. This was the concept or the born of the plenoptic eyepiece. Actually, we use a scheme or a design similar to that in conventional eyepiece, but as I said before, we replace the eyes by this microlens array. Our system needs to be arranged in such a way that the microlens array is placed at the exit pupil. Otherwise, we have these artifacts in the images, or these artifacts if the microlens array are behind, or these artifacts if the microlens array is in front. This is the correct way. Our system is limited by the numerical aperture of the system, but this limits the resolution, not the number or the kind of objective we can use. If we use a big aperture stop, that depends on the magnification or a numerical aperture of the objective, we have 5 views in a diameter of the stop aperture, or we could have 3 images in the diameter of the aperture stop. This is transposed in such a way that when we have a more micro lens, we have higher angular resolution, but worse spatial resolution. Actually, the system has a decrease in resolution that is 1/5 of the resolution of the objective in this case, or 1/3 of the resolution of the objective in this case. So now we are going to show you how to use our plenoptic eyepiece, and this will be done by my partner Nicolò. Thank you very much.
Okay, everybody, I am Nicolò Incardona. I will make a brief demonstration of the operation of the device. First of all, I wanted to show you the setup of the device. Let me share the screen. We have here our microscope, optical microscope. I prepared a sample stage. You can use your microscope as always. Select the field of view of interest, then focus the sample at will, and then just remove one of the eyepieces from the eyepiece board. Insert the plenoptic eyepiece and connect it to the computer through the USB cable. And then you can start to work with the plenoptic eyepiece. Yes, just 1 second because I think Ángel didn't have internet. 1 second if. Okay.
¿Eh?
Yeah.
¿La gente no se me ha oído?
No.
So this is the plenoptic eyepiece. We can put in this way, and this is a mechanism with which we can adjust the location, the place in which we locate the microlens array and the sensor to the exit pupil of the microscope and the plenoptic eyepiece.
Okay, I just run the software. Here you can see the software. Let me share the screen. This is the software dedicated to the device, to the plenoptic eyepiece. It is a beta version. As you can see, it is just a simple graphical user interface. You have some buttons here. Here there are the camera parameters. You can adjust the exposure time or the channel gain to make a white balance manually or automatically as you want. And here you can see the sample. They are cotton fibers stained with fluorescent dye. Here, what you see is just the streaming of the sensor. It is the central perspective view of the sample, as Ángel showed before with this device. What we register is different perspective of the sample with which we can extract 3D information. Here, what you are seeing is the central perspective. That is basically what you will see in the microscope, but with an extended depth of field. So we can pass to show the operation of the software. Here, in this window, what we can do is a real-time 3D reconstruction, and the software with the particular algorithm provides optical sectioning. Here, you can focus at will at different depths within the depth of field of the system. Just moving the slider, you can focus, as I said before, at different planes of the sample. Once you have selected the Z depth range, you can put it here and save the focal stack. That is basically a collection of focused images, the ones that you saw before. Or with this range, you can save a point cloud that you can use to see the 3D virtual point cloud in our visualizing software or in any other software for this task. Or what you can do is to calculate a depth map that is saved in this folder. This, for example, is a color map version of the depth map. You can see the different fibers that are represented depending on its depth. They are represented in a different color, from blue in the background to red in the foreground. Or with this button, what you can save is the elemental images that are the different perspective views of the sample. That are saved in another folder here. Now, what I'm going to show you is the visualizer software. I have to say that now we have two separated softwares, but we are integrating them. So the idea is not to copy-paste the images from one folder to another, but to can see, let's say, the different perspectives in real time instead of only the central image. Now, this is the sample we were looking at with the software. And these are the different perspective views. You can see a good amount of parallax between the views. You can solve the occlusions. It gives a good sensation of 3D of the depth of the different parts of the samples. In this case, with I forgot to say before, it is a 20x objective. We have 7 views. Sorry. Or with the visualizing software, you can use the central image and the depth map we calculated to get a 3D representation of the sample. Here you load the central image and the depth map. And you can see the 3D representation of the sample. You can move inside your sample. You can see it in the color map we saw before, and so on. Obviously, as I said before, this software will be integrated in these two software will be integrated in one. So the idea is that this kind of visualization will be in real time too. You can visualize the sample, the vector point cloud of the sample in real time. The system, as Ángel said before, works perfectly without the need to match the numerical aperture of the objective with the micro-lens array. We can switch here to a 10x, or we can switch to a 40x. Maybe the sample is too thick for the 40x, but what I wanted to show is that you, for example, you can show just one plane, and instead of moving the slider to select at will the plane of reconstruction, you can just focus your sample here and you obtain optical section. What we are doing now is to maintain a fixed plane of reconstruction and move the sample with our microscope stage. And you can see the different parts of the sample focused in the reconstructed plane. So what I wanted to show is that you can use these images with Fiji too, not only with our visualizer software. Here I have Fiji. I can go and load the focal stack, for example. Not this one. Sorry, I saved 40x focal stack. I wanted to save the 20x. And here it is the focal stack, for example. You can just use Fiji, all its plugins. You can make a 3D reconstruction of the sample from this focal stack you saved. As you can see, and so on. I think that's all for this sample. I can show you another sample we captured yesterday, for example. This is the focal stack with another sample that is fat tissue that a colleague left me. And with this, you can do the same as for the fibers. You can make a 3D reconstruction. This was captured with 40x. So as we were saying before, we can work with any objective with 10x, with 20x, a 40x, and you can switch the objective at your will. There's no need to change the microlens array and so on. I will show you a bright field image too, just to show that the system works with bright field samples too. We captured the condenser of a chip and did a 3D reconstruction. This is the focal stack of the condenser and the chip. We put the elemental images in the visualizer. In this case, it was a 10x objective. There was 454 perspective views. You can see there is a great amount of parallax. Also, we did a depth map from this image. And from this depth map, we created a 3D point cloud that we represented in another commercial software. This, as I showed you before, this was done with the central view and the depth map. We merged them to get a point cloud and then represented it in the software. Okay, that's all. Thank you.
So thank you very much. This is all we want to show you in this workshop. Our prototype, our product, how you can work with this product, and don't forget to visit our webpage at plenoptic.com and see how we are progressing. Thank you very much, and if you have any question, don't hesitate to ask me. Everything is clear for you. Any question? Uf, ¿dónde? No la veo. Investigué. ¿Dónde pone eso? No veo las cuestiones, tú. Chat. Aquí. Chat de sesión.
Pero,
Sí, ya la tengo.
está escribiendo.
¿Quién? ¿Ángel? Sorry. Don't please. Thanks. Invitation. Thanks, Ian. Ángel, tengo una pregunta, si posible. Thank you, Ian. Think it is possible to name a thin section of meteorites by this way? Think and construct 3D images 2D. So, Ozan Unsalan, thank you very much for your question. You are investigating meteoritos, but with a telescope or with a microscope. So, yes, that's good. So, I don't. I think that your question is about meteoritos with a microscope, not with a telescope. Yes. So yes. Actually, if you are using bright field, you can use our technology as with other techniques. So, well, we have a limit because actually, if we want to register a 3D image, we need some thick of the sample. So it is so thin in such a way we cannot see depth in the sample. Actually, we have not 3D information. So depends on the thing. Actually, for to compute a 3D image, we need a thick sample. So what does it mean thick? So depends on the magnification of the objective. For instance, you are using sorry.
30 microns.
Yes, 30 microns, for instance, is the depth of field of our system when you are using a 40 magnification objective. So in this case, with this objective, you can use you can take 3D images. I mean, Stefan Berger. Hi, Stefan. So, well, it performs well when we use a 20 magnification objective. We have a depth of field of 150 microns. So in this case, we can register 3D images in this thick. If the sample has 30 microns of thickness, we need to use a 40 magnification objective. So sorry. Isn't there, Stefan Berger, isn't there too much out of focus blur? Yes, so actually our system isn't a confocal microscope in which you pass the light through a pinhole. Then you avoid a pinhole, focus it in the object plane. So then you avoid a straight line. But our algorithm can reject not in at all, but in somehow we can reject a lot of background light. But we have not any sample, no? Here, no. This is no, las tengo ahí. Ah, sí, tengo las otras. A ver. Hi, Ian. What is solution loose compared with a normal microscope? Oh, well, now that we are sampling the we are sampling the numerical aperture, the effective numerical aperture of a objective. So let me share again my let me share again my. So this is the image of the stop aperture of the objective. In this case, this is the stop is 10 millimeters and the numerical aperture is 0.5. In this case, the stop aperture are 6 millimeters. Ah, no se ve. ¿Y ahora se ve? Sorry. Dejar de compartir. Ventana de aplicación. Esta. Compartir. Ahora sí, ¿no? Ahora sí. Okay. So as I was saying, we are imagining the aperture stop of the objective, that the aperture determines the numerical aperture of the objective, the aperture and the focal length of the objective. So we are imaging the stop aperture just in the plane of the micro lenses. So then, in somehow we are sampling the effective numerical aperture of the objective. So in that case, our effective numerical aperture for our plenoptic system is actually that given by this microlens. So we have a loss in resolution in this case of about 1/5. No, 1/5. In this case, we are sampling the numerical aperture of the objective, but with 3 microlenses in a diameter. So then we have a 1/3 of a loose resolution. I don't know if this answers your question. Ian asked about, no, actually, let me share again my screen. plenoptic, plenoptic, Nico?
Sí.
Vale. ¿Ahora se ve?
Sí, no.
What is called a plenoptic 2.0 is the focused plenoptic, is this. And this is the unfocused, this is the plenoptic 1.0, okay? We are using a new way of capturing light field images, not focusing the object plane in front or behind of the microlens array as in plenoptic 2.0, but actually projecting the object plane towards the infinity, toward an image plane at infinity, in such a way that microlenses always focus the object plane, the sample, in its focal plane. And what is the maximum focus range you can recover? Focus range, you are wondering about the depth of field or the maximum focal focus range, or the maximum, I don't understand, Ian, the question. Is the maximum focus range you can recover. The maximum focus range, I understand that this is the
depth of focus, I think. No?
yes, the depth of field of the microscope. So actually depends on the object, the magnification of the objective. But for a 20x objective, we can recover about 150 microns. And for a 4x magnification, 40 magnification objective, we can recover about 30 microns. So that these are actually these are experimental results. ¿Eh? Uy, no te he entendido. Thanks, Ian. Nice for hearing for you again. How long? So, well, any question? We need to So, ¿qué dice? Que se lo expliquemos aquí. Are you going to show and
Hello, can you hear me? Thumbs up. Thumbs up, Nico. Can you hear me? Yes. Okay. I just wanted to say to Stefan that that we've been trying to image the Arabidopsis seeds. We've been successful germinating them, but we just see the cells within the seed, not the rest of them. So that we encounter some troubles with that. So maybe, guys, I don't know if you can show the cells, if you can show these pictures. If not, we will contact again Stefan, and we will show him the pictures of the cells within the seed next week, for example, because maybe we are running out of time right now. So maybe next week we can show at least those cells from the seed. Okay. Okay. Thanks. Thanks to everyone. Thank you for attending this workshop. And if you have any other questions or do you want to know a little bit more, you can visit our website or write us an email. You will find all the information on the website, and we look forward to talking to you all, guys. Thank you.
Okay, thank you.
Okay.
Goodbye.
No estaba yendo, ¿no?